As we begin 4.6 on solving exponential and logarithmic equations, it's important for you to be able to do 4.4 really well, which is the understanding that exponential function and log function are the inverse of each other. Because if you understand that, it would be very easy for you to see how the concept carry over from exponential to log equations. This is a property that we already talked about in class, where property of equality for exponential equation is true when if the base is the same, then the exponent has to be the same in order for the two sides of the equation to be equal. Now, we already have done some questions in 4.4 that are using this concept. However, in the book, up to this point, the way they actually want you to work on a question like the solving for y in this natural log of y equals to x is that they actually want you to write it using the definition of log, which means this is actually saying base e to the x power equals to y. So they want to use definition of natural log to write the inverse. However, in class, we actually been using the idea of solving equations already by taking both sides to the e power and therefore canceling out the natural log. So the light blue method is actually using the definition of log, where the orange method is to actually use function of property of equality for logarithm. Here's another example. To solve for y, what they want you to, in the past, what they want you to use is to realize that log base e. So by definition of log base e of x will equal to y. This is by definition of exponential to log. However, using the property of equality for exponents and logarithm, you will see that you know that by taking natural log of both sides, the natural log and the e will cancel out and end up with e is equal to natural log of, or y is equal to natural log of x. Again, this is same as natural log of x. So again, the light blue way is using the definition, but the orange way is to actually use property of equality. Let's look at an example. So we already have seen questions like this before. Right now you have a base 4 on the left and a base 1/2 on the right. We want to change it both to base 2 by changing 4 to 2 squared, which is equal to 4. Oh, sorry. And we still have the x on the top. And instead of 1/2, we have 2 to the negative 1. Remember, negative 1 power is same as the inverse, which is same as 1/2, x to the negative 3. And then using the power, this becomes 2 to the 2x is equal to, again, power, 2 to the negative x plus 3. Notice I'm multiplying, which means I have to distribute the negative so that minus 3 becomes a positive 3. And then using the equality, property equality for exponential equations, we can say that 2x therefore have to equal to negative x plus 3, which means 3x is equal to 3, x is equal to 1. You can see that this one, when you plug into the 4, you get 4 is equal to that 1 go into the to the x becomes 1/2 to the negative 2, which is also 4. So it works. Let's try a problem. Let's just go ahead and try number 3. Go ahead and pause the video now. After you give it a try, you can look at my solution. Okay, here's number 3 on the guided practice. The common base with 81 and 3 is and 1/3 is 3, so I'm going to change this 81 to 3 to the 4th power, 3 minus x, equal to 3 to the negative 1 power, 5x minus 6. Multiply the 4 to 3 minus x, gives me 3, 12 minus 4x is equal to 3 minus 5x plus 6. Please make sure on the quiz and the test that you distribute your multiplication to the second term. And then since they both have the same base 3, I can simplify this to 12 minus 4x is equal to negative 5x plus 6, which means plus 5x on both sides, leave me with x on the left, minus 12 on both sides, gives me negative 6 on the right. So x is equal to negative 6. In this example, it's just trying to show you that you can also use the definition of log to simplify your equation, just like in 4.4, even if the two sides do not have the same base. For example, in this one, you have 4x equal to 11. You can use log base 4 on the bottom to cancel out the 4, which give you x is equal to log base 4 of 11. Okay, just like in section 4.4, but this time you're using equality property of exponential function instead of using definition of log. Now that we have done exponential equations, as you can imagine, the logarithmic equations are also the same. So if you have the same base for log, like here and here, then x will also have to equal to 7. So in this example, they both have base 5 as your log, which means you can simply write 4x minus 7 is equal to x plus 5, and therefore you can solve for x. In this example, even though you don't have log base 4 on both sides, but you can use the power of 4 to the power of to cancel out the log. So you can get 5x minus 1 is equal to 4 to the 3rd power. 5x minus 1 is equal to 64. 5x is equal to 65. X is equal to 13. However, the thing with log function is that the inside of log cannot be negative, because log function has a domain that's x greater than 0, which means when you solve for x, if you have a log expression in your equation, you have to make sure none of the x value will make the log negative. If so, that answer becomes extraneous. So in this problem, the first thing you need to do is use the properties that you learned from 4.5 to compress the log function, log expression into one log by combining the addition sign into multiplication, which means the left side of the equations become log of 2x times x minus 5. And then you can simplify a little bit further by distributing the 2x, so this becomes 2x squared minus 10x. Notice that I'm adding the parentheses around both terms, because otherwise the log will only be applied to the first term. This is equal to 2. Notice there's no base under the log, which means it's assumed that this is a base 10 log. I'm going to take both sides to the 10 to the power of the either side, which cancel out the log. That gives me 2x squared minus 10x is equal to 10 to the second power is 100. It's time to factor to solve. Equal to 0. Divide both sides by 2. You have x squared minus 5x minus 50 is equal to 0. So this is x minus 10, x plus 5, which means my answer is x equals to 10 and negative 5. So again, we need to check for extraneous solution. Come back to the original. If I plug in 10, I have 20x here, 20 here, and 5 here, which are both positive, so that's great. But when I put in negative 5, I have negative 10 here and negative 10 here, which breaks the log expression, which means negative 5 is an extraneous solution. So the only answer to this problem is the letter C. So let's give you a try on number 9. Go ahead and pause the video. When you're ready to see a solution, you can press play again. So number 9. First we have to compress the log expression here by changing this to common log of 5x times x minus 1 equals to 2. That's common log of 5x squared minus 5x. Again, you need the parentheses. And now I can take both sides to the 10 to the power of, which cancel out the common log. I have 5x squared minus 5x equal to 100. 5x squared minus 5x equal minus 100 equal to 0. Divide by 5 on both sides. I have x squared minus x minus 20 is equal to 0. X minus 5, x minus plus 4 equal to 0. X equal to either 5 or negative 4. It says negative 4 will make this term negative, and also this term as well, I guess. So negative 4 is extraneous. My only answer is x equal to 5. In this section, there's a fun application of exponential decay formula that measures it's called the Newton's law of cooling. That states for a cooling substance with initial temperature T0, the temperature T after T minute could be modeled by this equation, this formula. So this is how the CSI, when they find a dead body, they can measure the body temperature of the person and also the room temperature to do a calculation of how long that body has been dead. Because the initial temperature of a person when they first die would be, for example, 98 degrees, because that's the normal human temperature, and then the room temperature would be the environment, and then they can use the cooling rate of air, which is R, to figure out what T is, which is the number of minutes since the body has died and start to cool. So this is like CSI level stuff. But it's a fun question for us to actually use e to the RT. Now notice that, let's kind of take apart this equation a little bit more. We're trying to figure out when something becomes room temperature. As you can imagine, the bigger the difference the temperature is from the room temperature, the faster it will cool. And as an object gets closer to the room temperature, the change will become a little bit smaller and smaller, which is the exponential decay. Notice that this function is a e to the negative RT. That negative R makes it a decay function. T0 minus TR give us the initial difference of the temperature. So this would be your initial value. This would be your exponential decay. So how much is left of the difference to the current temperature? To the room temperature. So here's an example of a car that overheats at 280 degrees Fahrenheit, and it needs to be at 230 degrees in order for the car to run. The rate of cooling for the air is 0.0048. So by plugging into the equation, we want to know when is it going to be 230 degree, when it's 280 degree now, minus the 80 degree current room temperature that is, times e to the negative 0.0048 t is in minutes, plus the room temperature, which is 80. Now, even punching this in the calculator would be kind of a challenge. So let me show you how you need to simplify this equation first before you will be able to plug it into the calculator. So what we're doing basically, we're solving for t. We're going to minus 80 on both sides, which give you 150 is equal to, I'll go ahead and subtract that, 200e to the negative 0.0048 t. Divide both sides by 200 to cancel out the 200. That leaves me with 150 over 200 is same as 3 over 4 equal to e to the negative 0.0048 t. You take natural log of both sides, which means now my equation is negative 0.0048 t is equal to, that cancels out, natural log of 3 over 4. So now you can go to the calculator, typing 3 over 4, which is 0.75, press the natural log key, and then divide that by negative 0.004. T would equal to 60 minutes. Here's the homework that you will get time to work on in class tomorrow or on Monday. I will see you in class. Thank you for watching.